This is SpaceTime Series 25, Episode 30, for broadcast on the 11th of March 2022. Coming up on SpaceTime, a hot Jupiter's dark side revealed in detail for the first time, new measurements of the mass of the most common thing in the universe, neutrinos, and stand by for the March equinox. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have obtained the clearest view yet of the perpetual dark side of a hot Jupiter exoplanet that's tidally locked to its host star. The observations reported in the journal Nature Astronomy have been combined with measurements of the planet's permanent day side to provide the first detailed view of an exoplanet's global atmosphere. The study's lead author, Thomas Michael Evans from MIT, the Massachusetts Institute of Technology, says science is now moving beyond just taking isolated snapshots of specific regions of an exoplanet's atmosphere to one of studying them as three-dimensional systems. The planet at the centre of the new study is WASP 121b, a massive gas giant nearly twice the size of Jupiter. The planet is an ultra-hot Jupiter discovered in 2015 orbiting around a star 850 light-years away. WASP 121b orbits its host star in just 30 hours. That compares to the 88 Earth days it takes Mercury to orbit the Sun. Because it's so close to its host star, WASP 121b is tidally locked, with the same side always facing the star, permanently roasting, while the other side is in perpetual darkness, turned away forever to the blackness of space. Hot Jupiters have very bright day sides, and WASP 121b's night side is about 10 times fainter than its day side. Astronomers had previously detected water vapor, and they studied how the atmospheric temperature changes with altitude on the planet's day side. But this new study captures a far more detailed picture. The researchers were able to map the dramatic temperature changes from the day to the night side, and to see how these temperatures change with altitude. They also tracked the presence of water through the atmosphere to show for the first time how water circulates between the planet's day and night sides. While on Earth, water cycles first by evaporating, then condensing into clouds, then raining out, on WASP 121b, the water cycle is far more intense. On the day side, the atoms that make up water are quite literally ripped apart at temperatures of over 3000 Kelvin. These atoms eventually get blown around to the night side, where colder temperatures allow hydrogen and oxygen atoms to recombine into water molecules, which then blow back to the day side, where the cycle starts again. The authors have calculated that the planet's water cycle is sustained by winds that whip the atoms around the planet at speeds of more than 5 kilometers per second. That's over 18,000 kilometers an hour. And it would seem water isn't alone in circulating around this planet. The authors also found that the night side is cold enough to host exotic clouds of iron and corundum, a mineral that makes up rubies and sapphires. These clouds, like water vapor, may whip around the day side where high temperatures vaporize the metals to form a gas. On the way, exotic rain might be produced, such as liquid gems from the corundum clouds. The authors were also able to use a spectroscopic camera aboard NASA's Hubble Space Telescope to carry out further observations of WASP 121b. This instrument observes light from the planet and its host star, and then breaks that light down into its constituent wavelengths, the intensities of which give astronomers clues about the atmosphere's temperature and chemical composition. Through spectroscopic studies, scientists have observed atmospheric details on the day sides of many exoplanets. But doing the same for the night side of one of these planets is far trickier, as it requires watching for tiny changes in the planet's entire spectrum as it circles the star. So, astronomers observed WASP 121b throughout 2 full orbits, one in 2018 and another in 2019. The researchers looked through the spectroscopic data for a specific elemental line or spectral signature that indicated the presence of water vapor. They mapped how it changed at different parts of the planet's orbit, which encoded information about the atmospheric temperature at a given altitude. And they found that the day side ranges from 2500 Kelvin at its steepest observable layer up to 3500 Kelvin in its topmost layers. On the other hand, the night side ranged from 1800 Kelvin at its steepest layer up to 1500 in its upper atmosphere. Interestingly, the temperature profiles appeared to flip-flop, rising with altitude on the day side, what's called a thermal inversion in meteorological terms, and dropping with altitude on the night side. The authors then passed the temperature maps through various models that are likely to identify different chemicals likely to exist in the planet's atmosphere, given specific altitudes and temperatures. And this revealed the potential for metal clouds such as iron, corundum, and titanium on the night side. The authors also observed that the planet's hottest region is shifted to the east of the substellar region directly below the star, most likely due to extreme winds. So the gas gets heated up at the substellar point, but it's then getting blown eastwards before it can re-radiate that heat into space. From the size of the shift, Michael Evans and colleagues estimate that wind speeds clock in around 5 kilometers per second. As you'd expect, the authors have already reserved time on the James Webb Space Telescope to observe WASP 121b later this year, and hope to map changes not just in water vapour, but also carbon monoxide, which the scientists suspect should reside in the atmosphere. Current theories suggest that hot Jupiters form further out from their host stars, just like the gas giants of our solar system, and then they migrate inwards. The amount of carbon and oxygen in the atmosphere will provide clues about where these planets actually formed. This is SpaceTime. Still to come, new measurements for the mass of the most common piece of matter in the universe, the neutrino. And America launches a new weather satellite. All that and more still to come on SpaceTime. Scientists have determined that the mass of the neutrino is less than 0.8 electron volts. The findings, reported in the journal Nature Physics, will help researchers better understand the makeup of the universe and its evolution. Neutrinos are the most common elementary particle in the known universe. There are even more of them than photons, and they're arguably the most fascinating. They're generated through radioactive decay in stars, in supernovae, in nuclear explosions, in particle accelerators, and in atomic reactors. The neutrino is so named because it's electrically neutral, and because its rest mass is so small it was long thought to be zero. And because they have almost no mass, they're capable of being accelerated to almost the speed of light. Neutrinos come in 3 known types or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. Each has its own specific properties. But confusingly, the 3 flavors of neutrinos don't line up with the 3 mass species. It seems each of the 3 flavors is made up of a quantum mixture of all 3 mass species. So a particular tau neutrino, for example, has bits of all 3 mass species in it. And those different mass species allow neutrinos to oscillate between the 3 flavors. So an electron neutrino, produced say through beta decay reactions, can interact in a distant detector as a muon or tau neutrino. Are you confused yet? Don't worry, you will be. Although they have no electric charge, neutrinos do have corresponding antimatter counterparts, identified by their opposite chirality or handedness. Neutrinos interact with other matter only through gravity and through the weak nuclear force. In fact, they're so weakly interactive that several trillion of them are passing through you every second without you even realizing it. In cosmology, neutrinos play an important part in the formation of large-scale structures, while in particle physics, their very small mass sets them apart, pointing the way to new physical phenomena beyond the standard model, the very foundation stone of science's understanding of the universe. Now, these new measurements were undertaken by the International Catron Experiment at the Karlsruhe Institute of Technology, which has the world's most sensitive facility for measuring neutrinos. Scientists used the beta decay of tritium, an unstable hydrogen isotope, to determine the mass of the neutrino through the energy distribution of electrons released through the decay process. The 70-metre-long experiment houses the world's most intense tritium source, as well as a giant spectrometer to measure the energies of the decay electrons with unprecedented precision. To undertake these extreme measurements, each and every possible effect on the neutrino's mass, no matter how small, has to be identified and investigated in detail. An extremely laborious and intricate process, but the only way to exclude systematic bias in the results due to distorting processes. The experimental data from the first year of measurements and modelling allowed the study's authors to determine a new upper limit of 0.8 electron volts for the neutrino's mass. An electron volt is a basic unit of particle energy, the amount of energy gained or lost by a single electron accelerating from a rest state through an electric potential difference of 1 volt in a vacuum. It's the equivalent of 1.602 by 10 to the minus 19 joule. And thanks to Albert Einstein's famous mass-energy equivalence equation equals mc squared, that is, energy equals mass times the speed of light squared, it's also a unit of particle mass in physics and astronomy. Of course, March the 14th is Einstein's birthday, so we couldn't not mention him. This is the first time a direct neutrino mass experiment has entered the sub-electron volt mass range, which is vital in cosmology and particle physics, as it's here where the fundamental mass scale of neutrinos is assumed to be. Further measurements of the neutrino's mass will continue until the end of 2024. Scientists will steadily increase the statistics of events and continue to develop and install upgrades to further reduce the background rate. And the Karlsruhe facility is also working on a new detector called Tristan. This will allow Catherine to begin a search for the sterile neutrino, with masses in the kilo-electron volt range from 2025. Sterile neutrinos are one of the candidates for dark matter, a mysterious invisible substance which makes up 85% of all the matter in the universe, but which can only be detected through its gravitational influence on normal matter. This is SpaceTime. Still to come, a new weather satellite rockets into orbit. And the March equinox, the constellations Taurus the Bull, Leo the Lion, and the Gemini twins Poleax and Castor. And don't forget March 14, International Pi Day, and Albert Einstein's birthday. They're among the many features this month on Skywatch. America's newest weather satellite has successfully reached geostationary orbit. The mission flew aboard a United Launch Alliance Atlas V rocket from Space Launch Complex 41 at the Cape Canaveral Space Force Base in Florida.
Launch sequencer start.
Securing Centaur LH2.
Securing Centaur LO2.
So there we hear vehicles on internal. The auto sequencer is taken over and count.
FCS armed.
The flight termination system has been armed, and the team is continuing to finalize all preps as the vehicle is getting ready for liftoff.
FCS count started.
Reduce ECS for launch.
Roger. Vent valves locked.
And there we hear the vent valves locked, securing everything to secure that boil off. We should now be coming up on the last call for the range.
Rock, report range status.
Range green.
And there we have a green range, Daryl, so everything looks good this morning. Last but not least, we will bring everything to flight pressures and then hear that last status check.
Stable at step 3.
And there we verified that all pressures are good, and we are stable at step 3, ready for liftoff this morning.
Verify ECS reduced for launch.
Verify.
Status check.
Go Atlas.
Go Centaur. Go goes T.
And here we go. The final seconds now. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff. Liftoff of NOAA's GOES-T, our newest weather sentinel in the sky to help keep us safe here on the ground.
This look good. View has gone to closed loop control. The RD-180 is now throttling down as expected. Engine response looks good. We are now 33 seconds into flight. Atlas is 3 miles in altitude, 0.9 miles downrange distance. We have passed through Mach 1. Vehicle is now passing through max Q, maximum dynamic pressure.
Throttle back those RD-180s.
Now 55 seconds into flight. Atlas is 7 miles in altitude, 4 miles downrange distance, traveling at 1,900 miles per hour. RD-180 is now throttling back up.
They backed off the throttle to reduce
Now
the
at
stress
75
on the
seconds
rocket.
into flight. Atlas is 13 miles in altitude, 10 miles downrange distance, traveling at 2,700 miles per hour. Now at 90 seconds into flight, ULA's Atlas V rocket weighs now just one-half of what it did at launch, burning propellant at a rate of more than 2,600 pounds per second.
In 10 seconds, those solid rocket motors on the side will cut off.
SRBs have burned out as expected, and we see a good SRB jettison.
Here in a few seconds, they're going to throttle back up.
Vehicle performance looks good at this time, now 135 seconds into flight. The RD-180 has throttled down slightly. Vehicle performance continues to look good at this time. Tank pressures are stable, and Atlas booster battery voltages remain in their expected ranges. Now the upper stage is preparing for its use. Centaur reaction control system is now pressurizing to flight levels.
Now they'll jettison the payload fairing, which protects GOES-T at 3 minutes and 30 seconds.
We have just over 1 minute until BECO. We're now seeing the RD-180 throttle limiting to maintain a 2.5 G acceleration limit. Standing by for payload fairing jettison, and we've seen a successful payload fairing jettison. RD-180 is throttled back up now, and the vehicle has reached a 4.6 G acceleration limit and will maintain this level through BECO. We've seen that the Centaur has begun its boost phase shield down sequence.
Booster about to cut off.
And BECO, booster engine cutoff. Standing by for stage separation, and a successful stage separation event. We've seen pre-start on the RL-10, and Mass 1. We have ignition for the first burn. This first burn of ULA's Centaur upper stage will place the GOES-T spacecraft into a parking orbit around the Earth. This burn will last just over 7 minutes.
Operated by NASA and NOAA, the National Oceanographic and Atmospheric Administration, the Geostationary Operational Environmental Satellites, or GOES, provide continuous coverage of weather and hazardous environmental conditions across the United States. Once operational in a few months' time, the GOES-T spacecraft will be renamed GOES-18. The 2,857 kilogram spacecraft is the size of a school bus and carries enough fuel for a 15-year lifespan. Built by Lockheed Martin, it's the third of 4 new generation R-series weather satellites equipped with scientific instruments designed to monitor wildfires and floods across the United States. The first of the new satellites, launched in 2016, tracks Atlantic hurricanes and other East Coast phenomena, while the second flew in 2018. In fact, the pair were used to monitor the launch of their new sister. The fourth in the series is slated for launch in 2024. The GOES-18 will actually replace its predecessor, the GOES-17. That's the one launched in 2018. Problem is, it suffered a coolant line blockage, which has affected its main camera, causing it to lose up to 10% of its data due to overheating camera detectors. GOES-T, aka GOES-18, is equipped with a multi-channel infrared and visible light imager, a sounder which provides data for vertical atmospheric temperature and moisture profiles, surface and cloud top temperatures, and ozone distribution. A data collection system to receive and resend ground-based meteorological data from other weather stations, and a slew of scientific packages, including a magnetometer, an X-ray sensor, a high-energy proton and alpha particle detector, an energetic particle sensor, and a sun-pointed extreme ultraviolet sensor. The spacecraft also carries a search and rescue repeater. It collects data from emergency position indicating radio beacons and emergency locator transmitters, better known as EPIRBs, which are used during search and rescue operations. This is SpaceTime. And time now to turn our eyes to the skies and check out the celestial sphere for March on Skywatch. Happy New Year! Well, it would be if this was ancient Mesopotamia or Rome. That's because March was the first month of the new year, going back to the earliest concept of celebrating New Year's Day at the time of the vernal equinox, around 2000 BCE. See, the ancient Roman calendar, which had just 10 months, designated March 1st as the new year. That 10-month calendar is still reflected today, with the name September or Septem being Latin for 7, October or Octo meaning 8, November or Novem 9, and December or Deci meaning 10. It wasn't really until the Gregorian calendar that January 1st marked the start of the new year. But in the beginning it was mostly Catholic countries that adopted it. Protestant nations only gradually moved across, with the British, for example, not adopting the reformed calendar until 1752. Prior to that date, the British Empire and its American colonies still celebrated New Year's Day on March 25th. The highlight of the month is the March equinox, which this year takes place at 0233 hours on the morning of Sunday, March the 20th Australian Eastern Daylight Time. That's 11:33 on the morning of Sunday, March 20 US Eastern Daylight Time and 3:33 p.m. Greenwich Mean Time. For our listeners in the Northern Hemisphere, it means the vernal equinox, the start of spring, while those south of the equator, it's the autumnal equinox, meaning a move into autumn. The day marks the point in Earth's orbit around the Sun when the planet's rotational axis means the Sun will appear to rise exactly due east and set exactly due west to someone standing on the equator. It means almost equal hours of darkness and light. In fact, the very word equinox is derived from the Latin, meaning equus or equal, and nox meaning night. It all comes about because Earth's rotational axis is tilted at an angle of around 23.4 degrees in relation to the ecliptic, the plane created by Earth's orbit around the Sun. That axial tilt is always pointed at the same position in the sky, regardless of Earth's orbital position around the Sun. So, on any other day of the year, either the northern or southern hemisphere is tilted more towards the Sun. But on the two equinoxes, usually around March 21st and September 23rd each year, the tilt of Earth's axis is directly perpendicular to the Sun's rays. However, there's a complication called precession. This causes Earth's spin axis to wobble ever so slightly, just like the axle of a spinning top. The rate of precession is only about half a degree per century, so people don't notice it on human timescales. And because the direction of Earth's axis of rotation determines at which point in Earth's orbit the seasons occur, precession will cause a particular season, for example the Southern Hemisphere autumn, to occur at a slightly different place from year to year over a 21,000-year cycle. At the same time, Earth's orbit itself is subjected to small changes called perturbations. See, Earth's orbit's an ellipse, and there's a slow change in its orientation which gradually shifts the point of perihelion, Earth's closest orbital position to the Sun. Now, these two effects, the precession of the axis of rotation and the change in the orbit's orientation, work together to shift the seasons with respect to perihelion. And because we use a calendar year that's aligned to the occurrence of the seasons, the date of perihelion gradually regresses through a 21,000-year cycle. And there's another complication. Australia and some of the other Commonwealth countries start their seasons on the first day of the month, what are referred to as meteorological seasons, rather than on the solstices and equinoxes, which are referred to as astronomical seasons. So that means Australia's autumn officially began on March 1st rather than on the day of the March equinox. Meteorological seasons are used because it makes it easier for meteorologists and climatologists to break the seasons down into more exact 3-month calendar groupings for comparing seasonal and monthly statistics. The moment of the March equinox is also important in astronomy because it's used to define the celestial coordinate system of right ascension and declination. In astronomy, the celestial coordinate system is the astronomical equivalent to the latitude and longitudinal coordinates used on Earth's surface. It's used to specify the position of objects in three-dimensional space and the direction of those objects on the celestial sphere, the imaginary globe surrounding the Earth. In other words, it lets scientists determine the position of a celestial object, such as a satellite, a planet, stars, galaxies, and so on. Right ascension, which uses the symbol alpha, is the angular distance measured eastwards along the celestial equator from the vernal equinox. On the celestial sphere, it's analogous to terrestrial longitude. Declination, which uses the symbol delta, measures the angle north or south of the celestial equator, and so it's the celestial equivalent to terrestrial latitude. Marking the vernal equinox and setting the western evening sky this time of year is one of the oldest recognized constellations in the heavens, Taurus the Bull, so named around 6,000 years ago. In Greek mythology, Taurus represents the king of the god Zeus. Zeus lusted after King Agenor's daughter Europa, who was looking after a herd of cattle. Now, being a god and with godlike powers, Zeus decided to transform himself into a powerful white bull so that he could get closer to the beautiful Europa. Now, once transformed into a bull, Zeus convinced Europa to climb on his back, and he then carried her off to the island of Crete. Taurus's head is represented by a dominant V-shaped grouping of stars. The bright reddish star in the group is Aldebaran, an orange giant 1.5 times the mass of the Sun, located 65 light-years away. A light-year is about 10 trillion kilometres, the distance a photon can travel in a year at 300,000 kilometres per second. the speed of light in a vacuum, and the ultimate speed limit of the universe. Aldebaran is the 14th brightest star in the night sky and the closest bright star to the point of the vernal equinox. In ancient Arabic, Aldebaran's name means the follower, as it appears to follow the 7 sisters of the Pleiades. It's also the first of the 4 royal or guardian stars identified by the ancient Mesopotamians. Now, that V-shaped grouping of stars near Aldebaran is known as the Hyades. It's the nearest young open star cluster to Earth, located just 153 light-years away. Between Aldebaran and the Orion constellation, you'll see a bright red star. That's Betelgeuse, the 9th brightest star in the night sky, these days more commonly called Betelgeuse. If you turn to the north now, you'll see the 2 bright stars Pollux and Castor, which represent the northern constellation of Gemini, the twins. In Greek mythology, they were brothers who travelled with Jason aboard the ship Argo in search of the Golden Fleece. Pollux is an orange-hued evolved giant star, located 34 light-years away. It has about twice the Sun's mass and is bloated out to around 11 times the Sun's diameter. In 2006, an extrasolar planet or exoplanet, designated Pollux b, was discovered orbiting the star. The planet is a gas giant, orbiting its host star every 1.61 Earth-years. The other star, Castor, is located some 51 light-years away, and it's actually a system of 6 stars comprising 3 eclipsing binaries. Eclipsing binaries are binary star systems in which the orbital plane of the 2 stars in the system lies so nearly along the line of sight from the observer here on Earth that the stars appear to eclipse each other. Looking to the northeast now, and you'll see the star Regulus, or Little King, the brightest star in the constellation Leo the Lion. Leo is mentioned by Homer in his famous 8th century BCE poem, the Odyssey. According to Greek mythology, Leo was killed by Hercules as the first of his 12 labours. Located some 79 light-years away, Regulus is a multiple star system composed of at least 4 stars. Regulus A, designated Alpha Leonis, is a spectroscopic binary comprising a rapidly spinning Spectral Type B blue-white star, around 3.5 times more massive than the Sun, with some 288 times the Sun's luminosity, and a small companion star, most likely a white dwarf, the stellar corpse of what once would have been a Sun-like star. The pair take about 40 days to orbit each other. Spectroscopic binaries are double star systems orbiting each other so closely and at such an angle that they can only be visually separated, from our viewpoint here on Earth at least, by their spectroscopic signatures. Astronomers describe stars in terms of spectral types. It's a classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as Spectral Type O blue stars. They're followed by Spectral Type B blue-white stars, then Spectral Type A white stars, Spectral Type F whitish-yellow stars, then Spectral Type G yellow stars. That's where our Sun fits in. Then there's Spectral Type K orange stars, and the coolest and least massive of all stars are Spectral Type M red stars, commonly referred to as red dwarfs. Each spectral classification system is further subdivided using a numeric digit to represent temperature, with 0 being the hottest and 9 the coolest. And then you add a Roman numeral to represent luminosity. So, our Sun technically is a G2V or G25 yellow dwarf star. Also included in the stellar classification system are spectral types L, T and Y, which are assigned to failed stars known as brown dwarfs, some of which were born as Spectral Type M red dwarf stars but became brown dwarfs after losing some of their mass. Brown dwarfs fit into a unique category between the largest planets, which can have around 13 times the mass of Jupiter, and the smallest Spectral Type M red dwarf stars, which are around 75 to 80 times the mass of Jupiter, or about 0.08 solar masses. The primary star in Alpha Leonis completes a full rotation around its axis in under 16 hours. That's incredibly quick, especially when compared to our Sun's 30-day rotational period. Now, this gives the primary star an oblate appearance, and it causes what's known as gravity darkening, meaning its poles are considerably hotter and 5 times brighter per unit surface area than its equatorial region. Scientists estimate that if it were rotating just 15% faster, the star's gravity would be insufficient to hold it together, and it would literally spin itself apart. Located further away are Regulus B, C and D, which are all dim main sequence stars. Main sequence stars are those undergoing hydrogen fusion into helium in their core, like the Sun's currently doing. Regulus B and C are thought to orbit each other every 600 Earth years and are located around 5,000 astronomical units away from Regulus A. An astronomical unit is the average distance between the Earth and the Sun, around 150 million kilometres or 8.3 light minutes. Regulus B is a spectral type F white-yellow star, while its companion Regulus C is a small spectral type M red dwarf star. Regulus D is a bit more of a question mark. It's a dim star, and, at least from our point of view, it appears to be sharing motion across the sky with other members in the group. At the opposite end of the constellation of Regulus is the star Beta Leonis, or Denebula, the horse's tail. It's a luminous white star thought to be spectral type A, about half as bright as Regulus, and the third brightest star in the constellation Leo. Beta Leonis has about 1.8 times the mass of the Sun and about 15 times the Sun's luminosity. It's suspected of being a dwarf Cepheid or Eta Scuti type variable star, meaning its luminosity varies very slightly over a period of several hours due to pulsations on its surface. Also at the other end of Leo are the stars Theta and Iota Leonis, the loins of the lion. Theta Leonis is about 165 light-years away. It's a very young spectral type A white star, about 2.5 times the mass of the Sun. With an age of just 550 million years, Theta Leonis' spectra shows enhanced absorption lines for metals, that is, elements other than hydrogen and helium. This increased metallicity appears around 12% higher than the Sun, allowing the star to radiate with some 141 times the luminosity of the Sun from its outer atmosphere, at an effective temperature of 9,350 Kelvin, literally giving it a white-hot glow. Located some 79 light-years away, Iota Leonis is another spectroscopic binary, consisting of two stars orbiting each other every 183 Earth years. The primary star is a spectral type F yellow dwarf star, a little hotter and more massive than the Sun. Algebra, or Gamma Leonis, is a binary star system with a visible third component. The two primary stars are located 126 light-years away and can be resolved in a backyard telescope. Both are yellow giants, orbiting each other every 600 Earth days. The unrelated tertiary star, named 40 Leonis, is a yellow tinged star which can be seen through binoculars. Its traditional name, Algebra, means the forehead. Other stars in the system include Delta Leonis, or Zosma, which is a blue-white star 58 light-years from Earth, Epsilon Leonis, a yellow giant some 251 light-years from Earth, and Zeta Leonis, an optical triple star. The brightest component is a white giant about 260 light-years from Earth, while the second brightest star, 39 Leonis, is widely spaced and is located to the south of the primary, with the third and faintest star in the system, 35 Leonis, located to the north. Also located in Leo is Tau Leonis, visible as a double star through binoculars. It includes a yellow giant located some 621 light-years from Earth, and a binary secondary star 54 Leonis, a pair of blue-white stars divisible in small telescopes and located 289 light-years from Earth. Also in the constellation Leo, you'll find the Leo triplet, a group of three galaxies, Messier 65, Messier 66, and NGC 3628, all appearing relatively close together. Messier 65, also known as NGC 3623, is an intermediate spiral, possibly barred spiral galaxy, about 37 million light-years away. M65 disk appears to be slightly warped, and a relatively recent burst of star formation is suggestive of some gravitational interaction with the other two galaxies in the Leo triplet, possibly around 800 million years ago. Nearby is Messier 66, or NGC 3627. Another intermediate spiral galaxy, some 95,000 light-years wide and about 36 million light-years away. Gravitational interaction from its past encounters with the neighbouring galaxies in the triplet has resulted in an extremely high central mass concentration, a high molecular to atomic mass ratio, and a resolved non-rotating clump of neutral atomic hydrogen apparently removed from one of its spiral arms. The third member in the group is NGC 3628, the Hamburger Galaxy, a spiral galaxy with a spectacular 300,000 light-year long tidal trail of gas and stars. NGC 3628 is located 35 million light-years away. Its most conspicuous feature is the broad and obscuring band of dust located along the outer edge of its spiral arms, effectively transecting the galaxy to the view from Earth. Other bright well-known galaxies in Leo include Messier 95, Messier 96, Messier 105, and NGC 2903. M95 and M96 are both spiral galaxies, each about 20 million light-years from Earth. M95 is a barred spiral. Another barred spiral galaxy is NGC 2903, which is thought to be very similar in size and structure to our own Milky Way galaxy. It was discovered by William Herschel in 1784. Close to the M95-M96 pair is the elliptical galaxy M105, which is also around 20 million light-years from Earth. Okay, let's turn to the east now and the constellation of Corvus the Crow. In Greek mythology, Corvus was a really clever crow. In fact, he could talk to people. However, after refusing to speak to the god Apollo, he was banished to the sky, together with Crater the Cup and Hydra the Snake. One of the brightest stars in Hydra is Alphard, the solitary one, so named because it appears all alone in the sky. Okay, turning to the western horizon now, and you'll see the star Achernar in the southern tip of the constellation Eridanus the River. Eridanus is one of the largest and longest constellations in the sky. Achernar means the river's end, as it marks the end of the river Eridanus. Located around 139 light-years away, Achernar is a binary star system, comprising two stars, Alpha Eridani A and Alpha Eridani B. One of the 10 apparent brightest stars in the night sky, Alpha Eridani A is a young, hot spectral type B blue star, about 6.7 times the mass of the Sun, with a stunning 3,150 times the Sun's luminosity. Achenar's extremely high rotational velocity of over 16 kilometers per second gives it an oblate shape, making it one of the least spherical stars in the Milky Way, with an equatorial diameter some 56% greater than its polar diameter. This distorted shape means the star displays significant latitudinal temperature variations, with its polar temperature being above 20,000 Kelvin, while its equatorial temperature, being much further away from the stellar core, is only around 10,000 Kelvin. Those high polar temperatures are generating a fast polar wind, ejecting matter from the star and generating a polar envelope of hot gas and plasma. The companion star, Alpha Eridani B, appears to be a spectral type A white star with about twice the mass of the Sun. The two stars orbit each other at an average distance of roughly 12.3 astronomical units. Now, just a quick reminder that March 14th marks the yearly celebration of the mathematical constant pi. Pi is the ratio of a circle's circumference to its diameter. But it's also an irrational number, meaning its decimal representation never ends and never repeats. More than just a number, pi has important applications in astrophysics, orbital mechanics, and other fields of astronomy. It's been calculated to over 1 trillion digits, and the current record for reciting pi from memory is over 70,000 digits. Imagine sitting next to that person at a dinner party. As for me, 3.14159 is about it. Of course, as well as Pi Day, March 14 is also the birthday of the great Professor Dr. Albert Einstein. Jonathan Nally, the editor of Australian Sky and Telescope magazine, joins us now as we continue our tour through the March night skies.
G'day, Stuart. Well, March, we normally start, as you know, our tour of the sky with the south because there's lots of good things to see in the south, and I like the south. That's the southern part of the sky, that is, for the southern hemisphere. Lots of good stuff. You've got the Southern Cross and all those sorts of things. But this time we'll start with the view to the north and see what we can see in mid-latitudes in the southern hemisphere. If you're in the northern hemisphere, you've got to look to the south, of course. So we're in the southern hemisphere looking to the north. So low down in the north at the moment, you've got 4 constellations of the zodiac. There are 12 constellations of the zodiac, and you can see 4 of them really easily at the moment. You've got Taurus, you've got Gemini, Cancer, and Leo. Cancer and Leo, they look a bit bare, just to the unaided eye. If you go out and have a look at that area of the sky, you think it's not much there. But Gemini and Taurus look really, really good. They've got some really standout things. So you can easily tell Gemini, for instance, because it's 2 bright stars. Gemini is the constellation of the twins, so-called, and these 2 stars, Castor and Pollux, are very close together in sky terms, and they're not the same brightness, but they're close to the same brightness. And the interesting thing, because they are the 2 bright stars in the constellation of the twins, well, the star Pollux is actually a twin itself. It's a double star system, right? And Castor, the other one, it's not a double star system. It's a sextuple star system. There are 6 stars in this star group. To the unaided eye, you can only see 1, but there are actual 3 sets of double stars. So you've got a double star is where 2 stars are orbiting around each other. You've got 3 sets of those all orbiting around each other in this star Castor. So it's really quite amazing when you think about it. And, you know, they say that many, if not most stars out there in the universe probably are in double or triple or quadruple star systems or something like that, and single stars like our sun are a bit more of the oddity. And it also, of course, used to be thought that if you do have double stars and triple stars and whatever, what would that mean for the formation of planets around them? Would the gravitational field of the extra stars cause such a disturbance that planets wouldn't be able to form? And for a long time, this camp said, yeah, we don't think planets will be able to form around those stars.
That was a huge debate.
Well, we might be able to. Yeah, big debate. And then, of course, they started finding all these planets in other star systems, and even planets in multiple star systems. So it just goes to show that there's a lot happening out there, even in double stars.
Tatooine is there, out there somewhere.
Yeah, absolutely, yeah. So the science fiction authors tend to have a bit more imagination, perhaps, than that's probably not true. The science, by its nature, is, I guess, conservative, and scientists don't tend to stick their neck out too much, or if they do, they make it clear that they're sticking their neck out. And they don't.
There's always another scientist willing to chop it off if it's out too far.
So, like they say, if they say, look, I'm sticking my neck out here, and this might be the case, that's fine. But if they really be too dogmatic about it, they could, pride goeth before the fall, sort of thing. So what else we got? So Gemini, and we've got Taurus. Taurus is with its bright red star Aldebaran. Aldebaran is a single star, by the way, just on its own. Taurus and Gemini, both these constellations, have lots of great star clusters too, which you can easily pick out if you have a pair of binoculars. There are one or two star clusters that you can, or groupings of stars that you can see with the unaided eye, but if you get the binoculars onto them, you can see a lot more because you've got extra magnification. You're bringing in more light with the lenses in the binoculars. Higher up in the northern sky, you've got mighty Orion, our favourite constellation. Grab the opportunity to see it now if you're really keen on seeing Orion and all the great stuff that's in that constellation, because a couple of months from now, it'll have dropped below the western horizon, and we won't be able to see it again till towards the end of the year. Now, down in the south, high overhead at this time of the year, we've got the two brightest stars in the night sky. We've got Sirius and Canopus. Sirius, another double star system. The larger of its two stars is twice as massive as our sun, and that's not even particularly big, being twice as massive as our sun. There are stars out there that are far bigger than that, or far more massive than that. Sirius' apparent brightness, that's the brightness that it appears to our eye rather than its intrinsic brightness if you saw it from a standard distance. Sirius' apparent brightness is about twice that of Canopus, so it appears to be twice as bright as Canopus. But in fact, Canopus is about twice as massive as Sirius, and it's intrinsically much brighter itself. But Canopus seems dimmer just because it's a lot further away. Canopus is 310 light years from Earth, while Sirius is very nearby at only 8.6 light years. So that's another thing you need to bear in mind when you're looking at stars.
And your neighbour.
You think, well, that star is bright, so it must be close, and that star is dim, must be far away. That doesn't always work out that way. It could just be that star is bright because it's a long way away and it's really, really bright, but that dim star over there is very close. It just happens to be quite dim. That's the way it works a lot of the time. Sweeping south along the Milky Way, past Sirius and Canopus, we come to the far southern constellations. You've got the Southern Cross and you've got the Carina near next door. The Cross, this time of the year, in the mid-evening, it's lying on its left-hand side, okay? So it looks like a kite lying on its left-hand side. If you stay up late or you get up really early in the morning, about 2:30, 3 o'clock or so, you'll find it's much, much higher in the sky and standing straight up. And that's because the Earth has turned on its axis and our angle of the angle we're looking at it has changed a little bit, and therefore the sky has appeared to rotate, whereas in fact it's the Earth rotating underneath it. Now, shifting to the planets, and I'm afraid talking about getting up early in the morning, you're going to have to be a night owl or a very early riser to see any of them this month, because they're all visible to the east in the hours before sunrise. Venus and Mars are the first to rise, not too far apart from each other. You can easily tell them apart. In fact, you can't miss Venus because it's really big, really bright, and bright white colour. Mars nearby is an average sort of brightness, and it's got a reddish sort of tinge to it. So if you go out, have a look in the east a few hours before sunrise, and you see the biggest, brightest white light you can see, that's Venus, and the reddish-looking star in inverted commas nearby is Mars. A couple of hours after those two rise, also rising, we get Mercury and Saturn coming up over the horizon. Now, these two start off the month very close together in the sky. It just happens to be a line of sight thing. Our point of view from Earth sort of goes past Mercury, and into the far distance beyond Mercury, you've got Saturn. So they seem to be close together, but of course they're very far apart in the actual solar system. Mercury is the brighter of the two of those planets at the moment. It looks big and bright and white, and slightly dimmer Saturn has a yellowish tinge. You can always tell Saturn with that yellowish sort of tinge. As the days pass throughout this month, Venus and Mars, which started fairly close together, they're going to slowly move apart from each other. And Saturn and Mercury are going to really shoot away from each other as our line of sight to them changes. As we go around in our orbit, as Mercury goes around its orbit, and Saturn as well. And Mercury's going to start dropping lower and lower down towards the horizon, and eventually it'll disappear into the glare of the sun. And I haven't mentioned Jupiter yet, and that's because it starts the month in the same direction of the sun and therefore is lost in the sun's glare. We can't see it because it's around the other side of the sun. But by the end of the month, you should be able to spot it as well, poking its head up over the horizon shortly before sunrise, probably in a sort of pre-dawn glow. You'll see a brightish-looking white star, and that will be Jupiter.
That's Jonathan Alley, the editor of Australian Sky and Telescope magazine. And don't forget, if you're having trouble getting your copy of Australian Sky and Telescope magazine from your usual retailer because of the current lockdown and travel restrictions, you can always get a print or digital subscription and have the magazine delivered directly to your letterbox or inbox. Subscribing's easy. Just go to skyandtelescope.com.au. That's skyandtelescope.com.au, and you'll never be left in the dark again. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.